last lecture we have read some basic properties of set and mainly the operations on set. Today we will see some very useful properties on sets using the binary and the unary operations on the sets. And mainly these are the properties that are very useful to solve the problems using sets. So, first we list those properties and we can prove later all these properties. So, first thing is that some useful properties of sets. So, we consider 3 sets and a universal set U. So, let U be a universal set and A, B, C are 3 subsets of U. So, the following properties hold on A, B, C and U and all the operations that we read on set. And any of these property actually we can write as a theorem, since we can prove these properties also. So, the first property we give the serial number 1 and this is something called the, we call these properties as the laws, since we can prove this property. So, this is first is associative laws of set. So, we have operations on here we consider these 3 sets and the operations are union, intersection, and difference, set difference. We use this thing. So, associative laws we can write, if we take union of 2 A union B union C, this is same as that of A. Okay. If I take A union B union C, and for union operation whatever law is valid, that is true for intersection also. So, if we write, if we just replace union by intersection, we will get A intersection B intersection C, that is same as A intersection B intersection C. Now, we see the commutative laws. If I consider only 2 sets here, so A union B is B union A, and similarly I can tell A intersection B is B intersection A. So, if we continue, the third rule tells the important distributive laws on sets. we write that A intersection B union C is A intersection B union A intersection C. If we exchange the operations, that intersection and union, it is same A union B intersection A union C. Later we can prove these distributive laws. Now, identity laws. So, if I take the union of a set A with my null set, then we will be getting A only, because null set means this having no elements, and union is that elements which are either in A or in the null set. So, it is actually thus we can tell this is addition. Similarly, if I take A intersection with my universal set, then again this is the set itself. So, this is as if the identity. Now, I have the complement laws. So, A union A complement is the universe only, because if I take the subsets of A and A complement, that means all the elements of universe we are considering. Similarly, if I take A and intersection A bar, then this is actually a null set, because these are A and A complement are the disjoint sets having no common elements, they are disjoint. Then idempotent law. So, if I take A union A, which is A itself, similarly, if I take A intersection A, this is A itself. Seventh law, I can tell it gives something on the bound. So, this is the bound laws, either lower bound or the upper bound. So, A union with universal set is the upper bound, that the universe only. Similarly, if I take the A intersection with the null set, which is the lower bound, is the null set. Now, I have absorption. This is very much important when we try to simplify some set operations. So, absorption is A union A intersection B is A only. Similarly, if I exchange intersection and union, I will be getting A only. Now, involution. if we take the double negation of a complement of set, that means a complement of complement, that is the set itself. Then our something we call the 0-1 laws, that means the if I take the complement of my null set, that is nothing but my universal set, and if I take the complement of universal set, which is my empty set or the null set. I have another laws left, which is the our well known DeMorgans law on set. DeMorgans laws for set, and the operations are union and intersection and the complement. So, we can write that if I take A union B complement of that, I will get the A complement, union is replaced by intersection and B complement. Similarly, if it is A intersection B complement, this will be A complement union B complement, and we can prove. So, these 11 laws, these 11 laws on set, though we are telling these are the property, actually any one of this law we can prove this law on set, that we can prove logically. So, they are sometimes we call these are also the theorems on set. Now, we see that how to prove some property. First, we consider on say commutative law, the very simple one first we consider. So, this is my law 2, that we told that A union B is B union A, or A intersection B is the same as that of B intersection A. So, this is one set. Say first we the first part we take this one and we prove, we call this is part A, we call this is my part A, and we prove part 1 and we prove that thing. So, proof of part 1, and similarly we can prove part 2. How we can prove? So, see these are A union B, this is one set, similarly B union A is a set. So, let X be an element of A union B. So, how we can show that two sets are same? If we have to show that X equal to Y, then we have to that if X belongs to X implies X belongs to Y, and X belongs to Y implies X belongs to X for all X. For all X we have to prove this thing. So, first we say let X be an element of A union B. So, since X belongs to A union B, since it is a union, that means X is either X belongs to A or X belongs to B. because either A or B or both. So, I can write that x belongs to B or x belongs to A. That means, x belongs to same as that of x belongs to B union A. That means, if I consider that if x be an element of A union B, I have considered, then I have shown that x belongs to B union A also. So, that means, x belongs to A union B implies x belongs to B union A. Now, we have to show this is for all x, this is for all x. So, this is one we have shown. Now, we have to show that if I consider x belongs to, now the for the reverse one, that let x belongs to B union A. That means, again I can tell that x belongs to B or x belongs to A. So, I can again write x belongs to A or x belongs to B. So, I can write x belongs to A or B. So, what I can write that for all x that x belongs to B union A implies x belongs to A union B. So, this is my 2. So, for all x we can show the first one and from 1 and 2. So, I can tell from 1 and 2 that for all x that x belongs to B union A implies x belongs to, this is 2 and x belongs to A union B implies x belongs to B union A. So, I can tell that B union A equal to A union B. Similarly, I can prove that the intersection also. So, my commutative or commutative law of set, laws on set is proved. Okay. So, this is trivial. We prove the distributive law. Okay. We prove of distributive laws of set. Okay. Now, we write part 1 of the distributive laws, that A union or x A intersection B union C equal to A intersection B union A intersection C, or I can write A union B intersection C is A union B intersection A union C. Again similarly, I can tell this is my part 1 and this is my part 2. So, we prove the part 1. So, we take the proof of part 1. Again with the same logic, say I can tell my LHS, this is my x, this is my x, this is my y. So, x equal to y, we have to, the logic is that for all x we have to show that x belongs to x implies x belongs to y and x belongs to y implies x belongs to x. So, let x belongs to capital X means A intersection B union C. I have assumed that that means I can tell that what I have assumed x belongs to x, here x is A intersection B union C and y is that A union B, A intersection B union A intersection C. Okay. So, what does it mean physically that x belongs to A intersection? From the definition of intersection and union, since it is a intersection, that means, so x belongs to A and, because it is a intersection. So, this is and x belongs to B union C. Okay. So, x belongs to A, this is constant and, so it is there, I take this is always there. Now, from this x belongs to B union C, what we can write? Now, this it means that x belongs to B or x belongs to C. So, now if we consider, that means I have this and, that means if I consider, now I can write that x belongs to A and x belongs to B, or since x belongs to A and, so x belongs to A, or okay, this is and, or, and x belongs to C. So, this is one part, this is one part I can write. Now, this is and, again this is and, this is and this is or. So, I can write that x belongs to A and x belongs to B. The first I can write this equal to x belongs to A intersection B, since it is and x belongs to A intersection C, and these or I can replace by union. This should be a union. So, now what I get? X belongs to A union B, A intersection B, or that means union x belongs to C. So, how I can write this thing? How, if I now just write x belongs to A union B, that means A intersection B union A intersection C. So, I started that x belongs to, we have assumed let x belongs to A intersection B union C, and which implies that x belongs to, which implies that x belongs to A union intersection B union x intersection C. So, the first thing what we have assumed that means that x belongs to A intersection B union C implies x belongs to A intersection B union x belongs to A intersection C. That means these, and this is for all x, for all x. So, this is we get for all x, can tell for all x I get, this is one implication 1. Now, if I consider, let x belongs to A intersection B union A intersection C. Since from the definition of union, then I write that means, so the x belongs to A intersection B or x belongs to A intersection C. So, x belongs to A intersection B means x belongs to A and x belongs to B, and these are again I can write or x belongs to A and x belongs to C. So, again here we see that x belongs to A in both the cases, that x must be in A. So, I write this x belongs to A, both the cases it is there, and if I consider in this way, and this is here, this x belongs to B or x belongs to C. So, same as that I can write x belongs to A and together I can write this x belongs to B, since it is odd. So, it is union C. So, x belongs to B union C and x belongs to A. So, this is same as x belongs to A and means union and is intersection and is intersection, and this is B union C. So, what we have assumed? We assume that x belongs to this set and we infer that it implies that this. So, I can write now that, so we can get that for all x, x belongs to A union B union A intersection C implies x belongs to A B union C. So, this is my 2. So, since for all x, x implies x belongs to the A union B union C, remember that x belongs to capital X implies x belongs to capital Y, and x belongs to capital Y implies x belongs to capital X for all x, and then this is nothing but my x equal to y. So, here from 1 and 2, from 1 and 2 we can infer that my capital X is A intersection B union C, and capital Y is A intersection B union A intersection C. So, it is proved. So, my part 1 of my distributive laws of set is proved, and similarly we can prove the part 2 also. So, in this way any one of the 11 laws that we have enlisted, that we can prove. Quickly we can see the proof of DeMorgans law. Proof of 1 DeMorgans law. If I take the DeMorgans law, one part, that this is the law set. So, again I can similar way I can take that, let x belongs to, this is my capital X, say this is my x and this is my y. So, the similar way I can tell that this is A union B complement of. So, if x belongs to A union B, that means x does not belongs to A union B, because if it exists in the complement part, if I remember the Venn diagram also. So, this is this x must not be in that A union B. So, if I write, that means x does not belongs to A since it is union. So, or x does not belongs to B, that means x must not be in A or in B or anywhere in A or B. So, that means x belongs to A complement since we are in the universal set U. Similarly, I can take x belongs to B complement. So, what it means? That means x belongs to A complement, and here it will be and B complement. A complement and B complement, because x must not be in A, x must not be in B, that means x must be in A complement and must be in B complement. So, we can tell that when we have taken that x belongs to A union B complement, that implies x must be in A bar and x must be in B bar complement. That means x belongs to A union B implies x belongs to A bar intersection B bar. Or I can, other way I can, x belongs to capital X, because this is my capital X, that implies belongs to capital Y, and this is for all x we have done. So, this is one. Similarly, the same way, if I consider, let x belongs to A complement intersection B complement, since we have taken the union. So, this means x belongs to A bar or x belongs to B bar. Then x does not belongs to A and x does not belongs to B. So, x belongs to either A bar or B bar, that means x does not belong to A and x does not belongs to B. That means x does not belong to A and B. That means x does not belong to A intersection B. So, x belongs to A intersection B complement. So, x for all x, what we get, that x belongs to A bar B bar implies x belongs to A intersection B complement. So, this is my 2. So, again from 1 and 2 we can infer that x equal to y. That means x is my A intersection B union inverse is the, and that is A bar complement B bar, and this is the one part of DeMorgan is proved. So, in this way, that any one laws that we can prove using the elements of set, whether they exist in some set or whether they do not exist in the complement in this way. So, mainly from the concept of the set, the complement of a set and the 3 operations that we have read on the set, mainly the intersections, the union and the complement of the set. So, we have read the fundamentals of set, the operations, the basic definitions, and now we can proceed for that functions and relations using this set, where these basic concepts of sets are very much required. And as we have started with the discussion, that this is the very basic concept, the set is the very basic concept of any mathematical streams, mathematics, computer science or any discipline, we require this concept.